Okay, we'll get started. So happy Friday, everybody. Hope your day's going well. How's the homework? That's okay, more or less, sort of. Questions?
No.
Okay. Issues? Anybody? All right. Today we're going to review statistical inference. Seems a little out of place, but I don't know so not everybody here took Stats 10 here at UCLA. Some of you guys took AP Stats in high school, and or I don't know, you took something, right? Maybe an intro stats class at your community college or something. And so, I don't know, you guys chose to major in statistics, and which is great. I love statistics. But I don't, I guess in past quarters, I was always surprised at maybe sometimes I felt like some students lacked fundamental understanding of certain core concepts in statistics. I just want to kind of spend a day going over all of this stuff. If it's all review, then that's great. You're where you need to be, okay? And then if some of this is like, oh, I never thought of it that way, then I'm glad we had this lecture, okay? So I'm going to try to fit all of intro stats 10 into like one lecture today, all right? So I'm going to kind of fly through it, right? Normal quarter, you spend 10 weeks. I don't know if you were at community college, you spent 16 weeks on it or something, and AP Stats, you spent the whole school year, 180 days on it. So, 1 hour, that's what we get, okay? All right, so review of intro stats. Okay, so we start off, and this is usually like the very first thing you cover, right? The mean and the median, okay? And these are our measures of center. All right, and I don't know if anybody ever explained the conceptual ideas of the mean and the median. Usually it's like the median, you like start at the ends and you count your way into the middle, and then the mean, I don't know, you add them up and divide by n or something. But these are measures of center. The median, what that does is it balances the number of points that are higher or lower than the median, okay? And the mean balances the deviations of the points that are higher or lower, okay? And thus, because the mean considers how far the points are away, it's going to get pulled in the direction of the skew. So here's a little picture illustrating this. Here I've got the points 1, 2, 3, 4, 10, and 10, okay? So I've plotted them here, 1, 2, 3, 4, 10, and 10, and the median just balances the number of points. We've got 3 points below, 3 points above, okay? The mean, on the other hand, the mean is going to be 5 if you add all of these up. The deviations below are -1, -2, -3, -4 for these 4 points, okay? If it's 5, 4 has a deviation of -1, 3 has a deviation of -2, okay? So the deviations below add to -10, okay? And then we have two values at 10 and 10, and so we have a deviation of +5 and a deviation of +5. And the positive deviations, the deviations above, add up to 10. And so the mean balances those out. You got deviations adding up to -10 below, deviations adding up to +10 above, and the mean balances that out, okay? And it's kind of remarkable that the simple strategy of just adding up the numbers and dividing by how many you have performs this task of balancing the deviations. But that's how you can think of the mean and the median, okay? All right. And then the other part was measures of spread. So you have the variance and you have the standard deviation, okay? And so the variance you can think of as the average squared deviation from the mean. So these lengths are the deviations, and if you square each of them and you take the average, you would get the basically the variance, okay? Technically not the average because you divide by n minus 1, Bessel's correction, I don't know. You guys had to like prove that turned out to be a better unbiased estimator of the variance in 100B, right? Okay, all right. And what's the intuitive reason why you have to divide by n minus 1 versus n? Nobody? Okay. All right, so the intuitive reason why we divide by n minus 1 rather than n is because here we're measuring the deviations from the mean, right? And the problem is we don't know the population mean, okay? And so instead of the population mean, we're using the sample mean, okay? And so the sample mean is always going to be in the middle of your own sample, which is not necessary, whereas if you knew the population mean, it might be a little bit off, okay? And so your deviations from your own sample's mean are always going to be smaller than what the true population mean is going to be, right? I don't know if that makes sense, right? So over here, we're counting the deviations from my own sample's mean, but the true population mean could be like somewhere over here, right? And if I added up the deviations from the true population mean, the sum of those deviations or the sum of the squares of those deviations will be a little bit higher, okay? And then so Bessel's correction by dividing by n minus 1 rather than n compensates for that kind of adjustment, all right? So anyway, overall, larger values of variance and standard deviation mean the data are more spread out. Smaller values of variance and standard deviation mean the data are closer together, okay? All right, and then you guys learned about the normal distribution, okay? Unimodal, symmetric, and if the data is normal, what that basically means is most of the values are close to the middle, okay? And you've got the empirical rule, I should say 68% is within plus or minus 1 standard deviation, 95% is within 2 standard deviations, or more accurately 1.96, and about 99.7 is within plus or minus 3 standard deviations. They should all say approximately, okay? So that's your empirical rule. All right. The other key idea is we've got populations and we have samples, okay? Every research question has an associated population. The population is everyone relevant to answering the research question, all right? And the key idea is that the population is always too big to be studied directly, right? And you might not even know everyone, you might not even be able to identify everyone in the population, right? So tracking down the population is an enormous task, very expensive, right? So the United States does this with a census, and it's hard. They have to hire a whole bunch of people just to count people, okay? You know, we have to do it so we know how to properly allocate resources and stuff, but it's hard, okay? And then even then, we don't successfully track everybody because some people intentionally try to hide from being counted, okay? You know, it's like Sarah Connor or something. So, all right. But anyway, let's say your question is some experimental drug effective at treating disease JKL, right? So you've got maybe some new diseases out there, and you want to know, is this drug treatment effective, okay? Well, the population there is everyone who's got the disease, okay? And who has the disease? We don't know, right? That's a difficult population to track down, okay? So, okay, my picture got all messed up. Okay, I'll show you what the picture was supposed to. It's not that impressive of a picture, okay? In statistics, what we do is we select individuals from the population to be part of our sample, right? We're going to say, okay, well, I can't track down the entire population, but I'm going to study a sample, and based on what I see in the sample, we make conclusions about the population, okay? So basically, here's our population. This is supposed to be some big entity. This is too big for direct study. Okay, and then so what we do is we just select some individuals from the population, okay, wherever these are, right, and these all go into a sample, right? So that's what my picture was supposed to say, all right? Ideally, this sample that you look at is representative of the population, okay? And so you know, one method that's supposed to produce representative samples is random sampling, okay? And I don't know if your intro stats class told you that random sampling is hard, okay? Random sampling is hard, okay? And even if you're able to do random sampling is not guaranteed to produce representative samples, okay? I don't think we force you to take a class on sampling in your curriculum, right? You do experimental design. Have you guys had 101B yet? Yes? No? Okay. You probably have to do like an experiment on the island? Yeah? Maybe? Okay. All right. So in 101B, let me just give you the summary of the course, okay? So I would say there's kind of two faces to statistics, okay? Statistics is all about getting information out of your data, right? And this computational side, machine learning side, is kind of is useful for when data is abundant or there's like just way too much data and you have to kind of extract meaningful nuggets from your data, right? So it's like you know, computer generated data, you've got like streaming data, you've got Twitter things, and you just got so much of it, and you just need to cut through it, and you need the help of the computer to get through your data, okay? And so that's what all of this machine learning and computational stuff is for, okay? The other side is data is very expensive to obtain. So you have to think like a medical trial, right? So you're doing some drug testing, medical trial. Each observation you get in your medical trial probably costs thousands and thousands of dollars to just get a couple measurements, right? Because you need to get somebody to sign up and consent to all of this stuff. You need to get the medicine manufactured. You need doctors and nurses to take the measurements and records and stuff. Every single one of those observations, and usually it takes like 3 or 4 meetings of these things to just get one observation or like one thing, it costs thousands of dollars. And so you're lucky if you get, say, 30 observations, okay? And so 101B, the whole point is how do you get the most information out of a small set of data? If your data is difficult to obtain, how can you get statistically significant results from it, right? And so in 101B, when you do like the island experiment, I think the island is purposely designed to make random sampling almost impossible. You have to like go to each island and talk to the mayor or something and figure out some people to select. So they make it very difficult to get a random sample. It's like almost impossible to do so. And then when you like try to collect your data, they purposely put in a timer where it's like you click the button and you have to wait like 5 minutes to get your result, okay? And that's just the smallest inconvenience that they can do. So you don't say like, okay, let's gather data from 1,000 people, okay? It's just to kind of slow you down so that you'll say, okay, let's get data from like 40 people, and man, that took us a lot of time, okay? Because that's how it is in real life. If you're doing a medical trial, you might get 40 observations and it costs you like $40,000 just to get those 40 observations, and you need to analyze it, right? And you don't have the luxury of saying like, oh, let's just throw away all of this missing data, right? Like 15 people have missing values, so let's just throw them away. That's like $15,000 of effort wasted. So anyway, 101B is designing your experiment in the first place so that the little information you have can still result in possibly statistically significant result. Okay, so anyway, that's the other side of stats 101B. That was like one of my, I didn't come here for undergrad, but the design of experiments was like one of my favorite classes in undergrad. It's ultimately what led me here. Okay. Anyway, what was I saying? Oh, so random sampling, you get a sample, you're going to study your sample. We're hoping this sample is representative of the population, okay? And getting a representative sample is really hard. You can take an entire course. You can work for a company or organization like Pew Research, which does research in trying to figure out how to get a random sample. Like if I said get a random sample of UCLA students, how would you even do that? Yeah. So you say like, oh, I'm going to just stand outside on Bruin Walk. That will not get you a random sample, right? You're only going to get like people who walk on Bruin Walk, right? Which means people who go to classes, right? Which is not everybody, right? People who walk on Bruin Walk, which is not everybody, right? Some people like intentionally avoid Bruin Walk and things like that. And so, you know, if you think like, you just want to know who's part of a club, okay? You're going to get a biased sample, right? Because if you think like, oh, who are the people that avoid going to Bruin Walk? You know, there's probably a little bit of correlation between that and who may or may not join a club and stuff like that. So anyway. But anyway, we're going to pretend like we can take a random sample. And oftentimes, when you take a random sample, you calculate a summary statistic like the mean of the sample, right? But because the sampling process is random, we know that if we were to take another sample, we would end up with different values, and we would also get a different sample mean, right? And so the question is, well, what kind of values can I get for the mean of a sample, right? You know, and just thinking about it, we're going to say, okay, some values are more likely, other values are less likely, right? You check into just like a random sample, what's this average? And so the distribution of all possible values of the sample mean from all possible random samples is known as the sampling distribution of the mean, okay? You guys remember the sampling distribution and that concept? All right, from your intro stats class, all right, because that's key. All right, and you know, we could create one of these things via simulation, right? So you start with some hypothesized population. So you just arbitrarily say, you know, let's pretend that the population looks like this with this mean and this standard deviation. So I just chose the standard normal. I said, let's pretend the population is normal, has a mean of 0, standard deviation of 1, right? And then we're going to, we draw a random sample from this population, and then we calculate the mean of that sample, okay? And then we do this again. We draw another random sample from the population, we calculate the mean of that sample. We draw another random sample, calculate the mean of that random sample, okay? And we keep track of every single sample mean that we encounter, right? And after doing this, you know, thousands of times and keeping track of every single sample mean, we can get a sense of which sample means are highly likely to appear, what sample means are unlikely to appear, okay? And you can look at the distribution of those sample means, right? And then you learned the central limit theorem, I think, right? And what does the central limit theorem say? All right, loosely it says sampling distribution of the mean ends up normal, okay? As long as the sample is big enough, as long as it's randomly obtained, right? So random and independent. So this is just, so this represents the population standard normal, okay? And so, you know, I get values like -2, close to -2, high as -2. I think this is a sample of 16. A lot of values around between 1 and -1, okay? And then the mean of all of these values is very close to 0. It's like 0.1 or something, okay? Okay, here's another random sample from the standard normal, okay? So the population is standard normal, 16 other values, okay? You can see them in the rug plot and then the mean is somewhere else. Here's another random sample. Here's another random sample. And I did this a bunch of times, okay? So these are just different random samples, okay? And so this one I happened to get one particular value that was like really big, okay? Like 3 and then like a 3.5, which is a very high value to be drawn from the standard normal. But and so the mean ends up, way up here, okay? So I do this 10,000 times. I do 10,000 samples of 16 drawn from the standard normal, all right? For each sample, I calculate the sample mean, and I store it in the vector sample means, okay? So I say 10,000 of these things for I and sequence along, take 16 from the standard normal, calculate the mean of that, store that in sample means, okay? And if I calculate the mean of all of those sample means, I get something very close to 0. Now if I calculate the standard deviation of all of the sample means, I get something very close to 1/4, which would be 1 divided by the square root of 16, right? Which is what we expect. This is the sampling distribution of the mean, all right? And so, compared to the standard normal distribution, we see the spread here is a lot smaller, okay? The center is still at 0, okay? But almost all of our values are between negative 0.75 and positive 0.75, okay? Versus in the standard normal, you have to go out to like negative 3 and positive 3 to get almost all the values, okay? Here, almost all the values are between negative 0.75 and positive 0.75, right? Which reflects basically what the central limit theorem says, that larger samples, you're going to have less spread in those things. Okay, we can look at the QQ plot, and this is pretty much the perfect straight line. So we see that the sample means follow a normal distribution as well. Okay, and so provided that the sample is large enough, the central limit theorem establishes that the mean of a random sample comes from the normal distribution centered at mu, the population mean, with a standard deviation of sigma over the square root of n. Okay. The empirical rule tells us that 95% of the time, when you draw a random value from the normal distribution, it will be within 2 standard deviations of the mean. Okay, 95% probability. So what this says is, combining that, I say, when I draw a random sample, there's a 95% probability that the mean of the random sample will be within 2 standard deviations of the population mean. All right. So that's just applying the empirical rule here. Okay. And then you get the confidence interval, which is just taking that logic and working backwards, right? So here we said when I draw a random sample, there's a 95% chance that the mean of this random sample is within 2 standard deviations of the population mean. Okay. And now what we say is, when I observe a sample mean here, I can be 95% confident that the population mean is within 2 standard deviations of my sample mean, right? All right, and that forms the foundation of the confidence interval, right? The only problem is that the exact standard deviation sigma over the square root of n is unknown. So what do? We replace sigma with s. We just estimate it. We estimate what the standard deviation is using the standard deviation of our sample. But when you switch that introduces extra uncertainty. And so instead of the normal distribution, you use the t distribution, right? Is that all right? Okay. So question. Suddenly I got really loud. Question. Why do I say we can be 95% confident that the population mean mu is within 2 standard deviations of x bar, whereas over here I said there's a 95% probability that I can say x bar is within 2 standard deviations of the mean mu. So over here I can say there's a 95% probability that x bar will be within 2 standard deviations of mu, but over here I have to say I'm 95% confident, I can't say probability, I'm 95% confident that mu is within 2 standard deviations of x bar. So what's the difference?
Because you don't know the true population mean?
I mean, that's true. We don't know the true population mean mu, but I don't know what my next x bar is going to be either, right? So over here, I don't know what x bar is going to be, but I can say there's a 95% probability that x bar is going to be within 2 standard deviations of mu. Over here, I cannot say, at least from the frequentist perspective, right? When we go Bayesian, we can say probability stuff, but from the frequentist perspective, I cannot say there's a 95% probability that mu is within 2 standard deviations of x bar. I have to say I'm 95% confident that mu is within 2 standard deviations of x bar.
Oh, it's because it is or isn't? It is or it isn't,
right? So, okay. Is my question even making sense? Like, all right, so here's a thing. Okay, I've got a coin here, all right? It's a quarter. I'm going to ask you a question. What is the probability? I'm going to flip the coin. What's the probability it lands heads? Okay, not a trick question. You say 0.5, right? Okay. All right, so I flipped the coin, and I asked the question, what is the probability it landed heads? All right, and you guys still say 0.5? Okay, now watch what I do. Okay, all right. So I've looked at it, and I'm asking the same question. What is the probability that it landed heads? Okay, so some of you are saying 0.5, and some of you are saying 1 or 0. So it was a trick question, okay? The last 2 times that I asked the question, it was nonsense, right? Once the coin flipped and landed, there's no probability, right? There's no probability that it landed heads or tails. It either did or it didn't, right? Probability only exists for events of uncertain outcome, okay? Once the coin landed, there's no uncertainty, right? You don't know how it landed. You don't know how it landed, so you can say, I'm 50% confident that it's heads, okay? But it's incorrect to say there's a 50% probability that it landed heads because it either did or it didn't, right? So, so anyway, that's what we're saying. So the population mean mu is a fixed value, okay? And there's no uncertainty associated with it, okay? So we can only talk about us being 95% confident, okay, about whether it's in the interval or not, but we can't talk about there being a probability because it's either in the interval or it's not. There's no uncertainty associated with it, okay? All right, so anyway, this is your confidence interval stuff. All right, and then the other thing that you should have learned was hypothesis testing. And here we are approaching statistical inference from another approach, right? Instead, we say, let's imagine this hypothetical population with a hypothetical mean and a hypothetical standard deviation. So we're going to say, let's pretend this is what our population looks like. And we do, what could this population produce the observed sample that we have, right? So if in your mind, you believe that the average height of a human is 8 feet tall, okay? But we say, you know, there's some give or take randomness. Some people are taller and some people are shorter, right? And you I don't know, you're aliens from another world and you think, okay, the average height of a human is 8 feet tall, and you come and you visit Earth and you go, huh, could this be a random, you know, this is the classroom you see, no one here is 8 feet tall, and you go, well, could this just be a weird random sample, right? And then we would say, no, that probability of this happening just from random chance is wrong. Therefore, my hypothesis about humans having an average height of 8 feet is wrong. So anyway, let's just take a look at the t-test, right? So you have like the 2 independent sample t-test, and we take samples from 2 populations, and the question is, do the respective populations have the same mean or are they different, right? Okay, and so the null hypothesis is that there's no significant difference between the specified populations, and any difference that we observe in our data is just due to sampling error, okay? Sampling or measurement error, right? And then there's the p-value. The p-value, this is the definition that if you graduate in statistics and somebody later on asks you on the street, what's the p-value? And I don't think anybody ever will, but this is the answer you got to get, right? The p-value is the probability of obtaining a result equal to or more extreme than what's actually observed, okay? Assuming that the null hypothesis is true, right? All right, and the challenge is how do you explain a p-value to a 5-year-old or something, right? So that's it's the exercise. I'll put that. Probability of getting your data or something more extreme if the null hypothesis were true, right? Okay, and so here, what we do is we imagine two hypothetical populations. These two populations have the same mean, right? And when we randomly take samples from each population, if this hypothesis that the populations have the same mean is true, if that were true, when I take random samples, I would expect my random samples to have the same sample mean, okay? Or something close to each other, right? I would expect the difference between mean of sample 1 and mean of sample 2, I would expect that difference to be close to 0, okay? But of course, because it's random, it's not going to be exactly 0, but I would expect it to be close to 0. And so my actual data will have a difference of x bar 1 minus x bar 2, okay? That difference isn't 0, and the question is the difference I observed significantly different from 0, okay? And so to answer that, we calculate the p-value, right? If the two populations were equal, then what's the probability that random sampling would produce these two samples with, the observed difference or something even bigger than what we observed as a difference? All right. So here, my null hypothesis is that mu1 is equal to mu2. Let's just say sample 1 comes back with a mean of 10, sample 2 comes back with a mean of 12, okay? And the question is this difference of 2 points, is that difference significant, okay? And the answer is it depends, right? It depends on the standard error, right? If the standard error is really small, then maybe this difference of 2 points is like much bigger than the standard error, okay? And we would say that, this difference is significant, okay? On the other hand, if the standard error is very large, so this difference of 2 is only like 1.2 times the standard error, then this difference of 2 points is not significant, right? So, you have, in your intro stats class, I don't know, you might have spent time learning like the formulas for the standard error and stuff like that, but the idea here is just, what's the standard deviation of the sampling distribution? Here we're looking at the sampling distribution of x bar 1 minus x bar 2, and we just want to know, is there a lot of spread or not? Okay, we're expecting it to be around 0. We're getting 2. Is that significantly different from 0, right? So, so we do a p-value, right? So rather than just saying our observed difference is big or small, okay, we'll calculate a p-value, and it just quantifies the probability of observing our data or something more extreme when the null hypothesis is true. So if our p-value is small, it means that our observed difference is large, okay? That we're unlikely to get this difference of 2 from just random sampling alone, okay? And because it's unlikely to happen from random sampling alone, then I can conclude that my null hypothesis is not true and that there's something else contributing to why I observe this difference of 2, which would be unusual, okay? On the other hand, if the p-value comes back big, then it means getting this observed difference of 2 points is something that could happen just from random chance, okay? It's not an unlikely outcome if the only source of variation is random chance. So it doesn't prove that the null hypothesis is true, but we're not ready to eliminate the possibility that it is true and that our data was just a result of randomness. So this is kind of how you go, right? And so all of that stuff in your interest stats class, this was all under what we call parametric hypothesis tests, because it relies on the central limit theorem. It relies on this distribution, either this normal distribution or t-distribution, which is parameterized, right? Which has a mean, standard deviation, degrees of freedom, stuff like that, okay? So there's parameters that define these distributions, and so we call these parametric hypothesis tests, okay? And to work with these things, you have to use the central limit theorem and stuff like that, okay? And so on Monday, we'll come around and we'll start looking at randomization tests, okay? In randomization tests, we're going to start with kind of the null hypotheses, that there's no difference between the two groups, and they're going to rely on something called exchangeability, and we'll get into that, okay? But before we do, I just want to review a little bit about data collection, okay? How we obtained data will have implications for what kind of conclusions we can make, right? So, so this is just our setup, okay? Suppose a dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C, right? So does taking vitamin C reduce canker sores in the mouth? Okay. How can we get our data? We can get it from an observational study or from a random experiment, okay? And then the other part is, did we get a random sample or no random sample, right? All right, and so this is, we're going to do this a bunch of times. Okay, so here we're going to say we convince all the dental patients in town with appointments in the first 2 weeks in December to be subjects of a study, right? And then and we divide them into two groups: those who normally take 500 milligrams of vitamin C every day and those who don't, okay? And then we ask them how often they have canker sores in their mouth. We check their dental records to see who complained of canker sores. We compare the proportion of those who take vitamin C and complain about canker sores, and we compare that to the proportion of those who don't take vitamin C and complain about canker sores. And then let's say we find a, I have this spelled wrong, but let's say there is a difference between these two populations and it is statistically significant, okay? What kind of conclusions can we make, right? So first of all, is this a random sample? Okay, is this an observational study or an experiment? Okay, so no, not a random sample, and observational study, okay? So because it's not a random sample, you cannot generalize to the larger population, right? You can only make statements about these group of people, right? Observational study, you cannot make cause and effect conclusions. You cannot make causal inference, right? So we just know that for these patients, those who took vitamin C have fewer canker sores than those who don't, okay? We don't know why, and we don't know if this would be consistent with another group. We can't just generalize to the greater population. Now, you might be able to say those who made appointments in the first 2 weeks of December are representative of everyone else. That would be kind of a big assumption to make, and then you might be able to generalize, but in general, it's not a random sample, right? Okay, so over here, we're going to have same group, okay, or kind of some, right, patients in the first 2 weeks. But this time we randomly assign and we say half of you take vitamin C, half of you don't take vitamin C, and then we see who gets canker sores and who doesn't and stuff like that. We find a significant difference. What can we conclude? All right, so this time, still not a random sample, so we cannot generalize to the population, okay? But because the treatments were randomly assigned, this constitutes an experiment, okay? So the conclusion here is we don't know if this result would be consistent with another group, but we believe that we know why, that it's because of the vitamin C, okay? Because we've done the random assignment of the treatments. So because it's an experiment, we can make a cause and effect conclusion. Okay, on the flip side here, we take a random sample, okay? So we take a random sample of dental patients. We don't do random assignment. And so the conclusion here is that because it's a random sample, we can assume, or we can infer that the results that we obtain here will generalize to the general population. In this case, the general population would be all dental patients, right? Because we're getting a random sample of dental patients, we can only generalize to dental patients overall, okay? But because it's observational, we cannot make cause and effect conclusions, okay? And so, so whatever we find, we can say in those who take vitamin C will tend to have fewer canker sores than those who don't in the general population, but we can't make it a cause and effect conclusion. So maybe there's something else related to canker sore development and taking vitamin C. Who knows, okay? All right, and then the last one, which is a little overkill, is just if you have both random assignment and random sampling, then you can generalize to the full population and make a cause and effect conclusion, okay? Now this is almost, I don't want to say impossible, okay? But in general, this case where you have both random sampling and an experiment is almost impossible to obtain in real life, okay? Because with people, to participate in an experiment, you need consent, right? And you might have selected, you might have gone through the process of randomly selecting people and you went through all of that trouble, but if not every single person consents to join your experiment, it's no longer a random sample, right? So, especially if your if your experiment is related to like, are you suspicious of authority or something like that, then only, and you say have like who consents to do the experiment will obviously be different from those who don't consent to be part of the experiment, okay? And so, this scenario, this is like fantasy land for statisticians of having the random sample and the random experiment. This is very unlikely to happen in real life, okay? Oh, that's what I say, okay? So in general, you're often either working with random sampling only or with random assignment only, okay? And basically what you can do with either scenario will differ, okay? So we'll look at random assignment comes from experiments, random sampling comes from random sampling. So we'll take a look at this on Monday, okay? Have a good weekend, you guys.